Record, oh yeah.
Oh, yeah. Good job.
Just so that for the record, this class is starting a half an hour late because my Zoom would not work. So, so that nobody is seen as being late. So, yeah, this week we're going to be working with these various topics, and there will be a couple of other things. So I just wanted to do a quick review of the week. And let's back up here. And it starts off with equations in business. Now, not everyone is taking a business degree. For instance, Angela, you're doing healthcare administration, is that correct?
No, I'm doing business.
You're doing business, but you want to go into healthcare.
Yeah, I'm kind of, yeah.
Well, that's fine, because that actually gives you an expanded range of possibilities for this discussion.
Cool.
Because you will be doing a lot of things besides business. So what we're doing is we're looking at equations, which are statements of equality, statements of identity. An equation tells you that an equation that is an equation of equals has an equal sign in it, and it tells you that one side of that equal sign is exactly equivalent to the other. And that's the basis for solving these things. Now we can expand that. We'll talk about how that fits into inequalities later on this morning. But we have a lot of different equations that business uses. Some of the one example here is that of looking at total assets, which from your business class, you know, and your business accounting classes, you know, is liabilities plus equity. So that equation can be played with and rearranged as we did. We changed as it's written, the subject is total assets, and the components of that are liabilities and equity. But we can also calculate, if we knew the total assets, we could calculate, and the equity, we could calculate the liabilities. So we can rearrange that. So what we're doing is you're going to discuss two equations. It says the top two, that's up to you, but two equations that are likely to be important in your career, and two that you are not very likely to use. Now that's kind of that gives you a lot of latitude. And my post, which I put up last night, I don't try to go into your fields. In fact, I did something that was completely irrelevant to you guys. I looked at what I'm trained in formally, what my degrees are in, which is chemistry. And we use a lot of math in chemistry. And I gave two rather simple examples of equations that are continually used by chemists, and especially in my career in the pharmaceutical industry. When I started out, I was working in the lab and actually working at trying to invent new drugs. So we had a lot of calculations involved in that. So I also gave a couple out of business that I didn't think that I would ever use when I first started as a chemist. I have used them in my career, but that is a side issue. So let's see who else is here. Nathan, welcome. Glad you're here.
Hi, Nathan. I have a question about the discussion.
Sure.
Can you repeat it, like, and reword it for me? So you want to know two jobs that we would do?
No, just in your chosen field, what are two algebraic equations you might use on a regular basis?
Okay, that makes sense.
And then two that you don't think you'd ever use. And those don't actually have to be directly out of your field as far as I'm concerned. And
Okay.
then the crux of the discussion is why you should bother to know something you don't think you'll ever use. And I'm
Okay.
sure that you can relate to that. I'm sure you took lots of courses in high school that you said to yourself, I'll never use this junk. And yet you have, right? So, think about that. And it doesn't have to, as far as I'm concerned, they do not have to be in your field. So just don't pick my examples. All right.
Okay, so you want two algebra equations you would use in your career, two that you won't
Right.
use.
Or that you
And then,
don't think you will.
and then lastly,
Uh,
you want to write about?
Yep. Why do you need to know something you don't particularly see a need for?
Okay.
And let me give you one of my takes on that. When I went to school a long time ago, I studied chemistry because I wanted to be a scientist, a chemist. I went to work and I ended up moving around in the organization quite a bit. And in fact, I had basically four different, what you would call career tracks in areas that did not exist anywhere when I was in college. So what I'm saying is that life changes, you get opportunities, things develop that come out of nowhere, as far as we're concerned. And you may end up doing something completely unrelated to what you were trained in. I was trained as a chemist, and when I was in the pharmaceutical industry, I found myself negotiating contracts. Well, I never thought I'd ever do anything like that. And so what I'm saying is that you will find yourself doing things that you can't even imagine now. And the reason you can't imagine them is they don't exist, because the world is changing so quickly. So you may find yourself, so that is one of my takes on that particular issue. Okay, so that's the discussion for this week. That's going to involve some research. And what I'd like to do is set aside some time later on this morning for you guys to start that research so you can start looking for the information that you need. So let's go back. Now, your assignment, and that's another thing I'd like to set aside time, because actually your assignment is in many ways also related to the discussion. What the assignment is, and we won't go through all of the explanation here, you can read that on your own, but what the prompt for the assignment is that your employer requesting you design a study guide for your fellow employees to practice math skills. And you don't even know what skills everyone has. So here is what they want you to do: 10 formulas and look at your field and think about those. And that's where your research will come in. And 3 examples of each. Now, what that means is, let's just say you were a surveyor and wanting to calculate the size of a lot in a subdivision. And so the lot would be length of the lot and the width of the lot multiplied together. So we have area equals length times width. So your 3 examples might be just different lengths and widths to calculate that area. Okay, does that make sense? Okay. In other words, don't make it too complicated. You don't need to make it too complicated. We will be looking at the subject of polynomials, radicals, and inequalities this morning. So what we will do is do some of that work and then take a break for you to do some research. So this is basically a small paper, and you have a file upload here in one of the formats that's acceptable. Okay. And lastly, we have an assessment. So it's another graded quiz. I suggest you, I've taken a look at it. There's a lot of stuff in it. And you will not, as usual, you guys will not each have the same questions. You may not have the same questions at your various attempts. But you can have, again, 3 attempts to do this and to maximize your grade. And I would suggest you put off doing it until we've finished with our class on Wednesday, because of we'll cover a lot of that in the in-class exercises that we do. Okay. So, and then of course on Wednesday, we'll have an in-class exercise, an activity in class that will be related to our topics. So, questions? Okay, so let's take a look. I'd like to go up here to the course online resource. And I want to give you a bit of a warning. I don't know if you have looked at any of these videos yet, but you'll note that there is a transcript that you can download. It's kind of meaningless unless you've watched the video. The problem is there are errors in the transcript. So the videos should cover these things properly. We're not going to do the quadratic formula at the moment. That's advanced from here. But we will look at, we'll take a look here at this video right now on basic algebra formulas. Okay, everyone ready for that?
Yep.
Okay.
You have 2 options. The first one is AB. The second option is 2AB. If you could figure out the result is 2AB, excellent. Hello friends, welcome back to the Shortcut World. This is our new series where we are gonna cover every chapter, and this is our first chapter, Algebra. And today we are starting its part 1, which is basic algebra formulas. Oh, you call it formulae? Okay, no issues. According to me, both are correct. You say formulas or formulae, but we'll cover everything about basic algebra. So without wasting time, let's begin. The first formula is a plus b whole square, which is equal to a square plus 2ab plus b square. This is very basic formula, but still you will find many people doesn't understand how does it come. So if you also don't know how to prove this, simply multiply a plus b into a plus b. You'll get to know this. The next one is a minus b whole square, which is equal to a square minus 2ab plus b square. The next one is a square minus b square, which is equal to a minus b into a plus b. My dear friends, these are the most basic formula from which we can derive any other formula. So that's why let's revise it once again. The first one is a plus b whole square, which is equal to a square plus 2ab plus b square. The second is a minus b whole square, which is equal to a square minus 2ab plus b square. And the third one is a square minus b square, which is equal to a minus b into a plus b. Now we know all these 3 formulas, but Do we know what is the significance of this and how to utilize this in our practical life? Probably no. So let's say you have to find out the square of 52. How would you deal with this? My dear friends, let's use the first formula, a plus b whole square, which is equal to a square plus 2ab plus b square. If you compare here, a is equal to 50 and b is equal to 2. So simply we'll take the square of a, that means 50 square, which is 2500, and 2 into a into b. So 2 into 50 into 2, which is equal to 200. And at the end, b square, which means 2 square. 2 square is 4. Now simply add all this, 2500 plus 200 plus 4. It's 2704. That's it, my dear friends. This is as simple as this. Now let's try to modify the same formula which we had seen, which was a plus b whole square. If I try to write a plus b whole square is equal to a minus b whole square, now we need to do some modification in this so that this expression should be correct, right? Now if you look at the first part, a plus b whole square is equal to a square plus 2ab plus b square, right? The second part says a minus b whole square, which means a square minus 2ab plus b square. So if I simply add plus 4ab to the right hand side, this expression would be exactly equal to the left hand side, right? So now I can write a minus b whole square plus 4ab. So the similar thing can be done in the second expression as well. A minus b whole square, if I modify this in different manner, it would become a plus b whole square minus 4ab. This is what many people will say another formula, but this is exactly the same thing which we had written earlier. Or you can say this is just a modification of that. Now let's move on and try to figure out what would be the value of a plus b plus c. Let's say third variable is c, and if we are supposed to take the square of this, this is equal to the square of each variable, that means a square plus b square plus c square plus 2 into ab plus bc plus ca. That means 2 times of all this.
Okay, I stopped that because he's gone into an area that we're not going to touch on here.
Okay. Good, because I was about to have a brain aneurysm.
Yeah. And I'll just go ahead and say this directly. I hope that you understood what he said, but I'm going to go through this and show how this actually works when we're working with this. But those basic formulas are pretty important for us to know. And we'll go into we'll do some of that. Which
Just gonna say it. I didn't understand anything he said. So
yeah,
Angela, I'm kind of there with you. I was kind of getting it, and then I was like, okay, that kind of makes sense, but then why? And then it's going way too fast.
I'm with
Oh,
you guys.
when we get into later on, and probably toward the end of class, after you've had a chance to do some of your research for the discussion and the assignment, I'll go into that in more detail and hopefully explain it a little bit better than he did. I am not particularly enamored of his presentation, but he introduces an important thing, which is some basic formulas in algebra. And so what we have to do is learn how to solve those. So let me go on at this point, and I wanted to look at a little bit more with exponential expressions before we go there. And we'll come back to this topic, but that's a good introduction to it. And I'm sorry if that was confusing, but We'll clarify that. So I'm going to start with another share.
I think he just went too fast.
Yeah, that's one of the problems.
I agree.
Mine
He
kept
did speak
freezing on
very
the video.
quickly. He did speak very quickly.
And I like it to be broke down too. You
Right.
know, like break it down a little bit more for me so I
Tell
can
me why we're doing this.
explain yourself. I
Yes.
don't understand it.
Yeah.
This is
We
one
will
of the
get to that.
that I don't
I will cover that later on in this class. But let's talk about exponents first. And I have something that I hope is going to be a little clearer. Come on, why is this not working?
Technology doesn't like us today.
It really doesn't.
I know.
Can everyone see this exponents document?
Yes.
Yes.
Okay, good. So
I'm sorry, Mike, can you make it a little bit bigger for me?
sure,
Thank you.
that would be bigger for me too.
Thank you.
Is that good?
Much better.
All right. So an exponent is consists of the base and the exponent itself, an exponent term. We also call that the index or the power. So this is 8 raised to the second power, or 8 squared. We say squared if it's a 3 cubed, etc.
That's the same things, powered and squared. Oh,
X squared and x to the second power. If
okay.
it were 3, it would be x cubed or x to the third power.
Okay.
That's as far as we go. If this were a 4, we'd call it x to the fourth power or x to the fourth.
Okay.
And so that's what we say. So what this does is it tells us that if we line up 2 copies of 8 and then multiply them together, we get 8 squared or 64. Okay. So 5 cubed is 3 5s multiplied together. Think of it in that way. So you just write out 3 5s and put a multiply symbol between them. And then following PEMDAS, going left to right, go 5 times 5 equals 25, times 5 equals 125. Okay. And the fourth is the same thing, 2 to the 4th power or 2 to the 4th. And so we just line up 4 2s. So what this does is say that we look at the power or index or the exponent figure and just write down that many copies of the base. And it doesn't matter. We've started with integers, but it could be 12 times 12 times 12, etc. as well. But remember, the base is the entire number. So this is an 8 for ease, but it could be, you could have 4 or 5 digits here. And it works the same way. It's not the square of the last digit. It is the square of the whole number. Okay. And it doesn't have to be integers. It can be decimals as well.
Okay.
Okay. So you just line them up and multiply them out. You can do that. I suggest use your calculator. And in the scientific calculators, you can even specify the index. But one way to do it and get it right every time is just line up these numbers and make sure you put that many in place.
Do we have a scientific calculator on our computer?
Yeah, one of the arrangements, if you take a look at it, it gives you a choice. Let me just take a quick look at the one that's on mine.
Okay.
That has a standard calculator. And the choices that we have are scientific and other things and converters and stuff. So you have the scientific calculator there. Okay. So in general, we can represent an exponent as a variable raised to an index, a number. And by convention, we use the format of a to the n. And we will see a lot. It just tells us how many times a is going to be multiplied. So this goes out. So if n is 30, we'd be multiplying a times a times a. We do that 30 times. Okay. So n, this, remember from our discussion of sets, the ellipsis here just says that we keep going until we reach this limit. And the limit here is n, the number of terms. So if this is a to the fourth, it would be a times a times a times a.
Okay.
Okay, this is typical of math. We have general terms and we have specifics. Okay, so another way of writing it, of course, on your computer keyboard, rather than going through and trying to make a superscript, is to use the up caret symbol on the 6 of your of the keyboard, of the standard English keyboard. So 2 to the 4th, would be 2 caret 4. So we just again multiply that out. So we also we've been treating exponents as positive numbers, but they don't have to be. A negative is really 1 divided by, a negative exponent is 1 divided by the index to the power, positive power. So 8 to the minus 1 is, because 8 to the first power is 8, because you're not multiplying it by anything. Remember that little rule.
Because it's negative?
Yeah, here it's negative. We first figure out we first figure out the power, and
Okay.
then divide, and then what we do, invert it. Invert it means turn it over. Every number can be viewed as the number over 1. So when we invert it, it becomes 1 over that base, right?
Right.
Okay. So now we have 1/8. 8 to the minus 1 is 1 divided by 8. And so we just do that division, it's 0.125. So you can have a lot of those. And here is what I suggest. They suggest here you divide 1 by 5 3 times. That's a waste of time. We know how to calculate 5 cubed. We can look at this as 5 to the minus 3 can be looked at 1 over 5 to the minus 3. So the first thing we do is calculate 5 to the third and divide that into 1, and that becomes 0.008. Does that make sense?
In a way, yes. When it's laid out like that, and I kind of put it, yeah, kind of.
I will be posting this page in the shell after this class. I'll post all the pages that I've prepared in the shell for you to be able to review.
Okay,
Okay.
thank you.
Okay, so basically, again, to use our generalized notation, a to the minus n is 1 over a to the n. Good general form. So here's some examples. 4 to the minus 2 is 1 over 4 squared, or 1/16. And we just calculate the decimal. 10 to the minus 3 is 1 over 10 to the third power, which is 1 over 1,000. And minus 2 to the third. Now let's take a look at what happens. Let me see if we get down here. I want to talk about the powers of negative numbers. Remember that minus 2 squared is -2 times -2. Don't forget that sign. And we know that that becomes +4. So if we multiply it again by -2, we get -8. So here is a rule. Multiplying an even power, whether it's positive or negative, an even power of a negative number will give us a positive number because we are multiplying minus times minus and then minus times minus, etc. So that gives us a positive number. If it's an odd number, then the answer is going to be negative. So in this case, -2 to the -3rd is 1 divided by -2 to the 3rd, or 1 divided by -8, which, as we know, dividing a positive by a negative gives us a negative, and it's -0.125. So, but any power, whether it's positive or negative, of a negative number, the negative number will be enclosed in parentheses, because the difference is -2 to the 3rd is you multiply by -1 at the end. Now you're going to get the same answer, -8. But what if this was -2 squared? Well, 2 squared is 4, and the answer then would be, and then we have the minus that is separate. We're multiplying -1 times 2 to the 4th. So anytime we are raising a negative number to a power, it will be enclosed, the base, the not minus the index will be, or minus the base will be enclosed in parentheses. So that helps keep us from making the error of thinking. It tells us exactly where the negative sign is supposed to be. So we'll get some other examples of that later. If the exponent is 1, we already talked about that, then it's the number itself. 9 to the 1 is 9. Definition. If the exponent is 0, the answer is 1. It doesn't matter if we're talking about 9 or 999. If they're raised to the 0 power, it's 1 always. Okay. Now 0 to the 0 is a special case. We call it indeterminate because, you know, how can you raise 0 and suddenly create a 1? So that is not a number we can calculate. The answer indeterminate is commonly used for anything we cannot calculate in math. Okay, so let's take a look. We have some examples of powers of 5. 5 squared is 5 times 5, 25. 5 to the 1st is 5. 5 to the 0 is 1. 5 to the -1 is 1 over 5, or 0.2. 5 to the -2 is 1 over 25, 1 over 5 squared, or 0.04. Please use your calculators on these things. Now let's get over here. Here's a good example about what I was talking about before, grouping. We're raising -2 to the 2nd power. So that's -2 times -2, which is 4. But without the parenthesis, that means that we are raising 2 to the 2nd power and then multiplying it by the negative sign here. This implies a -1 times 2 squared. So then we get -4. Okay, we've got AB squared, again, is with parentheses around them. We multiply the product of AB by the product of AB. Without parentheses, this says A times B to the 2nd power. So this separates them out. So be very careful about this grouping. Look at the problem. Do not assume that this AB squared means that you're raising the power, you're raising A times B to the second power. Think about PEMDAS. This is A times B squared. The first thing we do is evaluate the exponent and then multiply by A. If we are in the parenthesis, we evaluate the A times B product first, and then raise that because we have to do the material in the parenthesis first, and then the exponent becomes what's done afterwards. That's why parenthesis is first in PEMDAS, because we don't want to be trying to raise something to a power without knowing what it is, right? We have to calculate that first. So does that make sense to everyone? Angela, you look a little confused. Do you have a problem with that?
No, that last part I do. Some of the stuff up there, I was a little confused. I get this part, but
Okay,
I think once I do it, I'll be okay.
Okay, what up further are you having trouble with?
It was really like I don't know. It was something up. Can you go up a little bit? I don't really remember. I guess I get all that. I don't know. If something comes up when I'm doing it, I'll let you know.
Okay,
Yeah,
that's fine.
I think it'll all come together.
Okay, good.
I have that same problem. I get really confused, and then I'm like, okay, that kind of makes
Once you
sense.
start doing it, yeah, that's how I am.
We'll make sure we do some of those problems, especially in the in-class exercise on Wednesday. There are some subtleties to math, and this is one of those. The grouping is a bit of a subtlety, and it's something you need to pay attention to. Once you do a couple of exercises with it, I think it'll be much more appropriate. Remember, we had some problems where we had like, 5 times 2 to the third was one of our PEMDAS problems last week. So think about this. There were no parentheses in that. So we were looking at 5 times 2 to the third. We raised 2 to the third power to make 8, right? And then multiplied by 5 to get 40. I think that was actually in the assignment last week.
I think you're right.
Yeah. So remember, so think of this always in terms of PEMDAS. If you keep PEMDAS at the top of your mind, it will make these things much simpler and much easier to understand. Same here with these parentheses. Just remember that there is a difference between a negative symbol inside the parenthesis and a negative symbol outside, which is where we've translated this to this. We've pulled the negative out as a -1 times 2 squared. Okay. And remember the implication. A plus by itself also can mean +1 times whatever follows it. A minus by itself without a constant behind it, without a number behind it directly, can mean -1 times whatever follows. Okay. If you're happy with that, let's try something else. Are you ready to go on to another topic?
Yeah.
Okay. Let me see if I can find the one I'm after. All right. Let's look at polynomials first. I think that will work. Nope, that won't work. I'll have to fix that when we take a break. Let me pull up something different. Inequalities. Let's look at inequalities. We've looked at equations, but inequalities are very common because not everything's equal. And we don't want everything to be equal. Let's give an example of an inequality. An inequality occurs when you are looking at calculating profit. You want there to be a difference between the sales and the expenses involved in generating a sale if you want profit. What we want is always for sales to be greater than costs. If they are less than costs, you're losing money. So that's an example, just a quick and silly, maybe silly example from business. But here's an idea. It tells us about what they're saying, relative size. But for example, here we have a race between two boys and one of them wins. What we don't know is how fast they ran, but we know that one was faster than the other. So we can say, in this case, we have Billy and Alex. So Billy is B and Alex is A. B is greater than A, faster. We can also reverse that and say that in the race, Billy's time was less than Alex's. And we could say B is less than A. So it depends on what we're talking about as well. Okay? They're not equal. They're inequalities because they are not equal. So the symbol that we use for inequalities is either greater than, which is an arrow head pointing to the right, or less than, which is an arrowhead pointing to the left. What that means is that in terms of greater than, it means that the number to the left of the inequality sign, of the greater than sign, is bigger, higher than the one to the right. So we'll get to some examples. There's a couple of ways of looking at that. This is kind of a nice little graphic. The bigger side has the wider space here, and the smaller side is a point, right? So Alex plays in the under 15 soccers. How old is he? Well, if it's the under 15 soccer team, he has to be less than 15. He can't be equal to 15 because it is the under 15. So our boundary condition here, and that's what equalities include, is what we call boundary conditions. Our boundary conditions is that he cannot be more than 15. He cannot be 15 itself. Okay, so he has to be less than that. We also have a symbol that we can say less than or equal to, or greater than or equal to. That means that our boundary, that if we want to include our boundary number, then we have it less or greater than or equal to, or less than or equal to. So in this case, we're saying that X is greater than or equal to 1, which means X can be 1 or anything above 1. In the absence of specifications, we're going to assume that these are all integers, but it can actually be anything from 1 to 1 point, up to 1.001. So that is also there. But if it's 0.99, then that's less than 1. less than or equal to, this case, y can be 3 or anything above. It can't be as much as 3.001. We don't round off. Okay, so you have to be 13 or older to watch a movie. So the equation here could be age greater than or equal to 13. We all know about those. So that's a quick introduction to inequalities. And I want to go and take a look at how we deal with them later. So that's what an inequality is. I want to go back. I want to go ahead and take a break now, so I can fix that other document that I was working on about polynomials. So let's take a break. I know we were supposed to take a break at 10, but we got started late. So let's take a break and we'll work on setting up the.
How long is the break?
Let's take 10 minutes.
Okay.
And remind me to restart the recording when we get back. And I have started the recording again. So we're going to talk now about polynomials. This is a word that simply means many terms. And remember, terms are any particular grouping connected by an operator or an equal sign. So a polynomial, this is 3 terms. 4xy squared is a term, 3x is a term, and 5 is a term. And in between them, we have operators. So this one has 3 terms. It's also called a trinomial because there are 3. So we can have constants like the 5. We can have variables like x and y, and we can have exponents. Okay. Okay. But only only positive exponents are generally seen in polynomials. But we don't divide by a variable. So in polynomials, we do not have 2 over x. Okay, can have all of these, but never division. So they can have more than one term, but not an infinite number of terms, because we have to have the ability to evaluate it. And there's no way to evaluate an infinite number of terms. So this is a polynomial. It is a polynomial of 4 terms. We have 5xy squared, 3x, 5y cubed, and 3. These are not, because we have a minus exponent, and then there's the other one we're dividing by x, by a term with a variable in it. So these things are also polynomials. This one is just 1 term. We call that a monomial, meaning 1 term. Mono meaning 1. This is a 2-term, a binomial, 2, x and 2. This is a binomial as well. I don't know why that is with an italic, but 79 times x.
My phone's not working.
Oh, this is 5. We do not have, we have monomials, binomials, and trinomials, but we don't have specific names for anything above 3 terms. So all of these are polynomials, even if it's just 1 term, and it can be just a constant. Okay, these are not because we have a -2 term. This one is not because we're dividing by a term with a variable in it. the x plus 2 in the parentheses is a term. The parenthesis tells us that. 1 over x is not the square root of x, because remember, another way of writing a square root is to give it a fraction for the exponent. So the square root of x is also can be written as x to the 1/2 power. Okay, x over 2 is allowed, 3x over 8, because you can divide by a constant. The square root of 2 is a constant. It just happens to be an irrational number, meaning an infinitely repeating number, an infinite decimal place that never repeats. So we have monomials, binomials, and trinomials. We don't use the term quadrinomial and quintinomial anymore. Used to be done, but not anymore. Okay. And then they can have no variables. 2L, 21 rather, is a polynomial. It has one term, which is a constant. It can have one variable, all x's, 3 terms, but only one variable. Why are they different terms? Because they are different exponents, 4, 2, and 1. Or more than one variable. You can have terms with 10 variables. Physics is famous for that, but we're not doing physics. Each of these is a different term, but there are 3 variables. So terms are the groupings that are separated by operators, and variables are just the letter terms for general designation. What is special? Well, we can find ourselves that we can do things with them. You can add polynomials to get another polynomial, usually with more terms, but not necessarily. You can multiply the polynomials and get a polynomial. It becomes a little bit, we're going to get into multiplying polynomials in a bit. So you can do a lot of additions and multiplications and still have a polynomial. We can graph them. If we have a value for x, say x is 0, 0 to the 4th is 0. 2 times 0 squared is 0, and 0 is 0. So if x is 0, the graph point, you've all done graphs before, is at 0. If we look at x equals 1, we get x 1 to the 4th is 1. 1 times 1 times 1 times 1. 2 times x squared is 2. And then x itself is 1. So we've got 1 minus 2 plus 1, that's 0. So we can see that the graph is 0 at this point where x is 1, the y value is 0, and so forth. Minus 1, we have x to the 4th. Minus 1 to the 4th is minus 1 times minus 1 times minus 1 times minus 1, which is plus 1. It's an equal number. Okay. Minus 2 times x squared. So minus 1 squared is 1 times 2 is 2, and then minus that. So we've got 1 minus 2 plus 1.
All the boxes are going up.
So so we can see that we can calculate all of these and plot these things out. We won't worry about that right now. they can be divided, but the result is not necessarily a polynomial. And the division process is not something we're going to do in this class either. The degree of the polynomial depends on the
Now, if you guys want to come back through the house,
largest
Sure.
exponent.
so suit yourselves.
Is the largest exponent that we have.
Oh, no, I wasn't meaning this way.
Oh.
There's too many.
Okay, the degree of the polynomial. So we look at the highest exponent
Going around, yeah.
in a variable.
Back through this way.
And so we have an exponent of 3 and an exponent of 1. So 3, this is the degree of this is 3. Okay. Standardly, but not necessarily, we put the highest exponent, the term with the highest exponent, on the far left. And we go down from there. So we've got an exponent of 3, an exponent of 1, and here there's no exponent. So this is a degree 3 expression. So the standard form, as I say, is we put the highest degree on first and then go down. So if we look at this 4-term polynomial, 3x squared minus 7 plus 4x cubed plus x to the 6th. 6 is the highest, so we put 6 to the left, then the cubed term, the squared term, etc. This makes things a little easier to deal with, so we generally say use the standard form. Okay. So does that make sense to everyone? So let's just find out for now if this is making sense to you, what these polynomials are. So a couple of things. Remember, we can have multiple variables in any terms, and we can have constants. But remember, we're not dividing by variables. We're not using negative or fractional exponents, or we're not using negative or fractional exponents on the variables. But we can use negative and fractional exponents on the constant, because those are constant terms. Constants are terms that have no variables. So in this case, 3 is a constant. The terms monomial, binomial, and trinomial are not are terms you will see, but they're definitional. Okay. So, questions, thoughts?
Not yet, but I'm sure when I'm applying it to the assignments, I might come up with questions. I think most of it makes sense. The part that kind of tricks me is the whole negative aspect to it, flipping it into the negatives. But like I said, I think when I'm applying it to actual problems that I'm working, it'll make more, it'll fall into place for me.
Okay. One way of looking at a reason that negative exponents are not acceptable is that if you remember, y to the minus 2 is 1 over y squared. So we'd be dividing 3x by y squared. And so since we can't divide by a variable, that's the explanation for why negative exponents are not acceptable.
Okay.
Okay. There's a lot of things like that to consider. Okay.
Okay.
All right. Got guys carrying furniture upstairs. Let me see what else I want to. Yes.
I might have to get off here because I have to contact my boss at Qdoba because I got an interview today at King Soopers, but I haven't told her that I have another job.
Ah.
So she's kind of at my throat right now.
Oops.
I have to go situate my job situation.
Okay.
Good luck on your interview.
Thank you.
Good luck.
I
Yes.
don't know how to
Good
tell them I'm
night.
gonna work 1 day a week. Oh,
Good
all right.
luck
Thank
with
you guys.
that.
Thank you. I'll talk to you
So
later.
I'll have the video posted later this afternoon.
Yeah, I'll be reviewing it.
Yep. Okay.
And I'll see you at tutoring.
Okay.
Okay, see you later.
Bye.
Thanks for letting me know.
Absolutely sorry.
No problem. So we talked about solving equations, moving things around. Remember, with an equation, you add, subtract, multiply, or divide both sides by the same thing, and you maintain the equality. Solving inequalities is the same basic principle, with a couple of funny little wrinkles that come when you are multiplying or dividing by negative numbers. Either of those operations actually reverses the inequality. So if you divide x plus 3 is greater than 2, if we were to divide each side by a negative, it would flip that. That greater than sign to a less than. But other than that, we can do that. Our aim in the same thing that we were looking at equations, and in my second discussion post of last week, I talked about solving equations. When we have an inequality is solved in much the same way. So what we want to do is isolate the variable to one side of the inequality. So if we have just a simple variable on the left by itself, then the inequality is solved. But if we have something like this example, x plus 2 is greater than 12, then we solve it the same way. We want x by itself. The way to do that is to subtract 2 from each side. So we get x plus 2 minus 2 is greater than 12 minus 2. And then these two cancel each other out, obviously. We subtract 2 from 12. So x is greater than 10. So that solves the inequality. That means that x is anywhere from 10.0000, et cetera, 1 to infinity, unless we put another boundary condition on it. So we solve things much the same way, but the direction of the inequality is something that does change with certain operations. So we have obviously the direction is which way the arrow points. So as shown, this is greater than. Okay, so the change of direction is that less than can become greater than, greater becomes less, and it solves for the less than or equal to and greater than or equal to concept as well. So make sure you make sure that you are aware of which direction this inequality is going. The safe things, the things that do not affect the direction, are either adding or subtracting a number from both sides, or multiplying or dividing both sides by a positive number. Okay. So simplifying a side also does not change anything. So we can simplify this example. 3x is less than 7 plus 3. We can add the 7 and 3 without changing the value of the direction of the inequality, become 3x is less than 10. But if we multiply or divide by a negative number, we will swap the direction of the inequality. Okay, all we do is flip it over. So if we are looking at 2y plus 7 is less than 12, if we switch the sides, in other words, rearrange it so that we are looking at 12, what that means is that 12 is actually greater than 2y plus 7. So if we reverse the sides of the equation, we also reverse reverse the sign. If we reverse the sides without changing anything else, okay? Adding and subtracting, we already know from the example above that if we subtract 3 from both sides of this example, x plus 3 is less than 7. If we subtract 3 from both sides, we're going to get x less than 4, and that is perfectly legitimate. All we have done is remove something. If we look at this on a number line, this example may or may not be very clear, but it does explain what happens. What we've done is pull 3 out of the equation. So instead of x plus 3, this becomes x. So we've actually just backed off on the number line to the left. That works well with adding and subtracting, assuming that we're adding the same amount to both sides. But what happens if x is on the wrong side? Let's look at an example of here. 12 is less than x plus 5. So we go ahead and isolate x and leave it there. And then we do that by subtracting 5 from both sides. So we get 7 is less than x. Now think about that for a minute. If 7 is less than x, then x is greater than 7. Think about that, because here all we've done to get x onto the left-hand side is reverse the equation. We swapped sides. So think about the logic of that. Again, if 7 is less than x, then x has to be greater than 7. So the inequality is still pointing at the smaller value. If we go up to this example at the very top, remember, big and small, this points, the point of the arrow is toward the smaller value. So in this particular case, the smaller value is 7. And then if we reverse it, we're still pointing to the smaller value. So remember that we can isolate either of these answers is correct and will work. But if we're looking at defining x as opposed to defining 7, then we want to have x on the left. Okay. Most of the time when we're solving equations, whether they're inequalities or equalities, we like to have the variable on the left. Okay. So if we want to multiply or divide by a positive number, it does not affect the inequality. So dividing 3y by 3 and 15 by 3 takes us to getting us y by itself. And again, we're looking for 1y. Remember, y by itself is an implication of 1 times y. So if we divide by 3, we get y is less than 5. And that is consistent here because we've divided by both sides by the same number. But if we're looking at negative numbers, then what we're going to be doing when we multiply or divide is reversing the inequality. Okay, so we have minus 2y is less than minus 8. So what we do is divide both sides by -2. And when we divide by minuses, we reverse the inequality. Now, -2 cancels out of both sides here so that we have y by itself. And it also cancels out on both sides. Remember, dividing a negative by a negative is a positive. So we have y then is greater than 4. Okay, the number line picture here shows that. -7 is, if we divide by -1, that -7 is less than -3, but 7 plus 7 is greater than +3. So we've divided both sides by -1 and come up with something that goes the other way. Does that make sense to everyone?
Yes, I think it does make sense, but it's still, for whatever reason, my brain still wants to be confused on it because it has negatives and positives in it.
Right.
I think I've got it though.
Okay. Again, we'll have some examples that we'll work on Wednesday when we do our in-class activity. Okay. What have we got here? Okay, Nathan, that's fine. Okay. So we can multiply and divide by variables as well. Okay. But this is another example. Bx, we've got two variables, is less than 3b. Okay. If we look at dividing both sides by b, then obviously cancels out on both and we get x less than 3. But if b is negative, it reverses the inequality. But if we don't know the sign of b, we can't solve this. Okay, what we have is two possible answers. X, depending on the value of b, x can either be less than or greater than 3. Okay, so but we don't know. So we don't try to divide by a variable unless you know that it's always some defined value. Okay. Okay, so we've got, there's obviously a little error here. Let me take a quick look now. Okay. This should be 3 divided by 2. So x minus 3 divided by 2 is less than -5. That is a mistake there. Let me see if I can. Whoops, I don't want that. Okay, let's get that fixed. Okay, we want to clear that by multiplying both sides by 2. Okay, because we're multiplying by 2, we are obviously they've got a mistake here, and I didn't catch this before. So this is actually should be in parentheses. Okay, and this obviously should be in parentheses. Okay. So I fixed that. This will now make a lot more sense. If we are dividing x minus 3 by 2 is less than -5, so we're now going to multiply by 2. So now we're going to, if we multiply x minus 3 divided by 2 times 2, we are actually clearing that fraction. 2 times x minus 3 over 2 is x minus 3. And then we are multiplying -5 by 2 to get -10. So now we have we solve it by adding 3 to both sides. We have x minus 3 plus 3 and minus 10 plus 3. Remember, adding a minus and a plus, we're going to end up with in this particular case, we're adding 3 to minus 10, so that moves it to minus 7. So x is less than minus 7. Okay. I mentioned boundary conditions at one point. We can establish boundary conditions by giving a pair of inequalities. We can say that minus 2 is less than this. Obviously, we have another error here that didn't come through to me. Let's fix that. Okay. Minus 2 is less than 6 minus 2x over 3, which is less than 4. What this says is that this expression, 6 minus 2x over 3, lies between minus 2 and plus 4. Minus 2 and plus 4 are boundaries on the potential value of this expression here in the middle. Okay, so we're going to multiply by 3 first to get rid, and let's get this division sign in here and make that clear. We're going to multiply by 3 first. And let me quickly save that. We're going to multiply by 3 first and get minus 6. Minus 3, minus 2 times 3 is minus 6, is less than 6 minus 2x, is less than 3 times 4, or 12. Now we have to subtract 6 from both sides of both inequality symbols. Okay, so we are going to subtract 6 from minus 6. We're going to subtract 6 from 6 minus 2x, and we're going to subtract 6 from 12. So that gives us minus 6 is minus 12, is less than minus 2x, is less than 6. So now we are going to divide each part by 2. And we're going to divide it by 2 so that we don't reverse the negatives yet. We can also do this by dividing by minus 2. But I want to show that we can divide by 2, and then we have minus 6 is less than minus x is less than 3. Now we're going to convert x to a positive number. And we can do this one of 2 ways. We can either multiply or divide by a negative number, by negative 1. In which case, again, we flip both of these inequality signs, and we get 6 is greater than x, which is greater than minus 3. So x lies between minus 3 and 6. Does that make sense? It's a lot to see in a complicated thing. You may want to study that, but does that make sense to everyone, what I did?
In the now divided each part by 2, it says that it's still a negative x, even though there isn't a 2 in there.
Right, it's still, but this is minus 2x. So if we divide by 2 plus 2, that doesn't change the sign.
Okay.
It's still a minus. So when we divide us by 2, notice that we divided by 2, we didn't change the sign on the minus 12, right?
Mm-hmm. Well,
So when we divided by 2, it's still a minus 12 divided by 2, which is minus 6. Okay, Anna, go ahead.
On the first part here, it says that it's negative 6 thinks it is greater than, right, or something. But it 6
is less than
2x, and then it's a positive 12 on the end.
Yeah.
and then you
Yeah,
subtract 6 from each side or each part. And okay, my brain went blank there. I was thinking the positive 12 on the end here for you flipping it, but I see what you did. Never mind.
okay. Great.
I got it.
Angela and Jennifer, you okay?
Yeah, I think so.
Okay, good. All right, so we have our, again, sometimes they want us to reverse it if we, it's not necessary to reverse this and put the smaller number on the left. That's these guys' idea of standard notation, but it's not required. Okay. So basically, we handle inequalities the same way we handle equality equations, with the wrinkle that if we multiply or divide by a negative number, or if we swap sides, if we flip the equation completely over, then we change the direction of the inequalities. Okay. Okay. We and remember that we don't multiply or divide by a variable. Sorry about that. You guys are having a hard time with, I've got a 10-foot long bookcase downstairs that got damaged. So they have to knock it apart. So sorry about the noise. Okay.
Bookcases aren't cheap.
No, but hopefully my insurance will help me.
Yeah, so we moved. My mom and I moved, and we lost about 5 bookcases, and we haven't been able to replace them. So it's a little
They are
pricey.
expensive. They are expensive. Even cinder block and board bookcases are expensive anymore. That used to be the cheap alternative. Okay, so what I'm going to do is let you guys get started on your research for the assignment and the discussion. And I'll mute my mic so you're not going to be listening to bang bang. If you have any questions, just ask them and I'll unmute and talk to you. And I'm going to continue to record just in case we have questions coming along, okay? So go ahead and get started on research for the discussion and the assignment. And I'll be here.
I cannot find a website worth anything for computer science and technology for equations that are mostly used. You're still muted.
Did you just go online and do a search, or did you go into the library link?
I didn't go into the library link. I went on to Google and searched it, but I know how many results that can be to search through.
Yeah, so what I did is I went into the library link, and I've been doing some searching, but there was a lot of information, especially under like the scholarly journals. And if you do a search where it does trade journals too, it might give you a few more ideas.
Yeah.
I like to get my sources from the library tool, and I don't have to spend so much time going through and like verifying the website, and like it cuts the work down in half really when you don't have to research so much on the source itself.
Yeah. I'm trying to figure out how to phrase this too, so it's so much fun.
Yes, that's a tricky part too. You have to definitely use the right search words.
Yeah, search strategies can get tricky. And think back on some of your courses you've had with people like Terry and John. They probably introduced you to some things that need to be calculated, and a couple of those. Some of the accounting courses, accounting is just a series of calculations and formulas. So you can also go into some of those arenas. Does that make sense?
Nope.
Yeah,
But
the last class I had with John, there was a bunch of stuff in there that fits right in with this.
Okay, which class was that, Jennifer?
It was, oh gosh, I had business law, but it wasn't that. I think it was, I don't remember the name of the class, but we were studying like the stock market and figuring up mortgage rates and stuff like that.
Was that economics, business economics?
Yes, that would be it. Yes, that sounds right.
There's an area that works out pretty well. So if you think about some of those other classes you've taken, and I don't know, Anna, what you may have taken in the past. I don't know how far you are into your program.
I started when Jen started, actually.
So we're right at it, almost a year. Got another month to go and we'll be hitting our 1 year.
Okay.
Wow. But yeah, mainly everybody in this class, we started at the same time.
Right. Okay. So
So
you should have had much of the same coursework.
I haven't had oh my word, my brain hurts.
The econ course.
I've had economics, I believe.
Okay.
Had my computer servicing 1 and 2 class. And I haven't had accounting, so.
You haven't had accounting. Okay.
I don't think I have to take accounting, so.
You might not. So that might be something that you just take a quick look at, equations in accounting, because you're not likely to have to use it.
Yep. Except for with the programming, it uses everything for computer programming. So
It certainly does.
So you can't get around not using an equation from algebra or trigonometry or any of the.
Yeah, you have a lot of choices there then. And as I said, don't make it complicated. Take a look at my posting on the discussion, and I make a point of not making things more complex than they need to be. And I use a little cartoon to inject a bit of humor into it. So,
Yeah, my brain doesn't do that. It makes it more complicated so I can solve it at a slower pace for some reason.
yeah. In reality, most of the material, most of the algebra you're going to use, especially in business and in reality, most of life is not going to be very complicated. The IT going into computer programming depends on what you're programming. If you're programming for business, it's just basically addition, subtraction, multiplication, and division. There's not a whole lot else. If you're programming if you're programming to do scientific analysis, say statistical analysis of data, then it gets more complex.
Yeah, it gets more complex when you are wanting to create an alarm for a store where it'll lock the doors before you even get out the door.
Sure.
That is my plan.
Ah,
Yeah. I've seen so many people run out of Ross during the holiday and a little bit after the holiday with baskets full of stuff. So I was thinking about creating something that if they pass through the little security things, that it'll shut the doors and lock them so they can't get out.
well, yeah, that would work in a lot of places.
Yeah. And then if a customer is walking out and they have just bought their stuff but we forgot a tag, it'll still do the same thing. However, you'll have like a little wand to scan the bag and it'll tell you which item you missed and you can pick up the item and remove it.
Right.
And that way people aren't going home with security tags still on their clothes. It has happened.
It's easy to do. I've turned around and walked back into stores before.
Yep.
So
Some people, I don't know why all the new people do this. Even I did it once, and then I was told that's the wrong thing to do. But with kid clothing, the two-piece or more, we have to security tag all of them together.
right.
And and sometimes people security tag it twice or 3 times.
Oh,
One per item.
eek.
Are you talking about the sensors that you put on the items?
Yeah. Yep. That when you pass by the door, it goes beep, 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 beep,
Yes,
beep.
it goes to
Yeah.
you put 2 sensors on each item.
Yeah, especially when cashiers are only looking for one.
Yeah, so our rule at my work is we make sure that the sensors go right at, like, we take the price tag and we punch the sensor through the price tag onto the item so that the cashier doesn't have, like, they have to scan that barcode anyhow. So the
Yeah.
sensor's right there at the barcode so they can't miss it. Because
Yeah, however, with
new cashiers always forget a sensor and customers beep at the door and then they have to come back. But it happens like daily at our work.
yeah, however, when it's kid clothing, it has to be on the side of it, on the left side. So when you're hard tagging it, you're hard tagging it from your right.
Oh, wow.
And so it's not through the tag because the tag is at the collar part for most of them.
Oh,
And so when we're hard tagging it, we have to get all of the pieces in that hard tag.
that could be difficult.
It is. I've poked myself more times than anything hard tagging back there. I've even poked myself to the point where I was standing there, you're talking with my coworker, and then all of a sudden I poked myself and ah, and I've completely froze because it was
Yeah.
it was literally about 2 centimeters in my finger.
Ouch.
Yeah.
Yeah, I've poked myself too with the sensors. It's no fun.
And trying to get them out of a really tight spot too, you can always poke yourself there too.
Yeah.
It's not so much fun, but with the technology that I want to create for stores, they'll be able to know which item was missed in a bag. That way we're not searching through it like maniacs trying to find it.
Yeah.
And it'll also
Good
tell us
idea.
if there's items in there that is not supposed to be in there, which means that the security tags are in a coat pocket.
Or on the floor in the fitting room.
Oh, I found about 15 security tags in a coat pocket.
Yeah,
And-
we found them there too. But we find most of them when we're cleaning if we don't have an attendant at the fitting room, they take advantage of that. And we find sensors in the fitting rooms, or they'll take the jewelry in there and steal it off the cards.
Yeah, we always have an attending at the fitting room. But I walked by the men's shoes department once, found about 20 hard tags, 10 of the screamers, and some of them were the ink ones.
Yeah,
So I was like, really?
I know. We find stuff like that too. And it gets really bad because we're in the mall, and Sundays is like the day that every junior high kid goes to the mall.
Where do you work?
Forever 21.
Oh, you're near Ross in there for.
Yeah, you're out in the parking lot, huh?
I'm actually in the one in Loveland in Centera,
Oh.
but I have gone to the one over in Fort Collins. It's a lot messier than mine, to tell
Yeah.
you the truth. I was like, what is this?
So you guys are probably all laid off right now too, aren't you?
Yeah, I'm hating it.
Yeah. But enjoy all that time that you get to spend with your little one, because they grow up so fast. You blink your eye and all of a sudden they're in their 20s.
Oh, I know. I'm trying, and we've been hanging out, and he's getting a new bed today, but he and I are going up to the mountains and to a cabin for 3 days, which is the reason why I was like, I don't know if I'll have internet.
Yeah,
'Cause
that'll
this
be
is
a
my
night.
first time I have ever been on a trip.
You said Estes Park, right?
Yeah.
Very cool. There's
Nothing else.
It's beautiful up there. It's just, it'll be nice to be in the mountain air for you.
Yeah. I always have liked the mountains, just not snow. I hate snow. I hate snow so bad. I grew up here and I can't stand the snow because it brings out all the crazy people,
Yeah. I
especially.
lived on top of a mountain for so long that down here it doesn't even seem like there's snow because it melts. Like up there, I was asking my daughter the other day if the snow started melting. She said it's finally starting to melt. Like they're out at the top of 119 in Golden Gate Canyon in
Mhm.
that subdivision. She said the dirt road's finally clear, but they've been in snowpack since October.
Yeah, I don't know if my car will make it, but I'm crossing my fingers. I'm
You'll do
hoping it will.
fine. It's all clear now.
Well, my car, since this is my new car, I haven't driven it to the mountains. And so my last car, you couldn't even drive it in the mountains or even get into like a certain area of the mountains because it would die on the hill.
Oh, no.
Yeah. So I am hoping this car makes it.
It will. Just have faith.
But I will get my discussion board post done and my assignment done. I will try to do that before Wednesday. But I am drawing a blank for right now for the discussion and the assignments. My brain is at the moment. So, and my battery is about to die too on my laptop. So, yeah.
Okay, well, what I'd suggest following Jennifer's suggestion about using the library resources as well.
Yeah.
You can, yeah, you can, and think about some of your other classes that you may have had some calculation or some formulas or so forth. Or think about how you might go about developing a formula for your idea about the about the alarm system for RFID tags,
Yeah.
and how you might program timing and everything else, because you know you'd want to maybe yeah, just think about how you'd want that to work. Think about if it happened to you, what you'd like to see. But you know, come up with a formula. You know, there are lots of things. You know, you're moving into a specialized area, so make up your own.
Okay.
That should work. At least
Yeah.
I'll be happy with it. I mean, I'm the one that's going to grade it. So.
Okay. All right. I do have to go, however, because I still have to pack my son's stuff. And
Have a good trip.
thank you. I will
Okay.
hopefully see you guys
Yeah.
on Wednesday.
Have a safe trip. Estes had a lot of rain over the weekend, so.
We did here.
Yep, we certainly did last night.
Oh, yeah. And hail. We had hail.
Oh, I missed that. I don't think we had it because my cherry tree and my tulips are still intact.
It was like pea-sized hail. That was it. Yeah. And it only lasted for about 10 minutes and it stopped.
Okay. Well, I'm glad of that.
I hope you guys have a good day, and I'll try and be on here on Wednesday. If not, I will watch the recording.
Okay, so yeah, be on time, or be here if you can. Have a safe trip, please. We really want you not to get, hurt.
Yeah.
And your son. And
Yeah.
meanwhile, so you have a safe trip, and Jennifer, I'm going to bring up some more information about polynomials. Do you want to take a short break or?
Okay. Yeah, I'll go take a break, go check on Herman and.
Yeah, please.
Okay.
Okay, when you're back, we'll pick it up. I've got a document on adding and subtracting polynomials.
Okay, sounds good. See you in about 10 minutes, maybe?
Sounds good.
Okay.
Okay, Jennifer, are you ready?
Oh yeah, sorry I had my mute. Yes, I'm ready.
All right, let me go ahead and share the screen on this. There we go. Can you see that?
Yes, I do now, yes.
Okay, great. Adding and subtracting polynomials. So we won't go through the term. What we will do is talk about the concept of like terms. that's where all the variables and their exponents are the same. The coefficients can be different, okay? So 7x and x and minus 2x and pi times x are all like terms because the variables are x and all of these, even pi, is a constant, right?
Okay.
So these are like terms because the variables are all x times y squared. So it's just the constant, you know, we've got a third or a half or whatever. All of these are like terms.
Okay.
Things that aren't like terms are things with either not the same variables or different exponents. So 2x and 2x squared are different.
Mhm.
2y and 2 times xy are different. So the purpose here is that when we are adding and subtracting polynomials, we will combine the like terms so that if we have one polynomial with a term of 2x and another polynomial with a term of 5x, we'll add those to get 7x. Right?
Okay.
So a couple of steps. We can place all the terms together to do this stepwise. So we're adding here 2x squared plus 6x plus 5, and then we're adding 3x squared minus 2x minus 1. So if we group those like terms, we've got two terms with x squared. So we've got 2x squared plus 3x squared. We've got two terms with x, so we have plus 6x minus 2x, and then we have two constants, 5 minus 1. So when we combine those, we get 5x squared plus 4x plus 4.
That makes a lot of sense with the organization of it, putting those like terms together.
And although this won't appear in what I post in the shell because I can't get the animation into a document.
Okay.
Let's take a look at how this shows in animation. Okay. So we don't have any, so there was just one constant term, so it just carries down. So did that make sense?
Yep, sure does.
Okay, another thing we can do is set them up as columns. And that actually may make more sense for a lot of people.
It does. That method there, it seems more natural to me.
And use whatever works. I'm very much toward the practical in this class. So you use what works for you.
Okay.
It also makes it easier, especially if you have complicated equations, and you can rearrange them when you make them into columns to make that a lot easier. So here's a trinomial and two trinomials and a binomial, and we can see that we have a bunch of different terms. We have an xy term, we have y terms, and we have constants. So if again, what they did was just set this up as a column. There was an x here, but none there, so it goes off to the side, and just line them up. And then that makes it quite easy to come up with this as our answer. Okay, so let's do a subtraction. I'll do the animation first. Okay, now this may have been a little confusing. So let's look at PEMDAS. PEMDAS tells us we clear the parenthesis first.
Mhm.
So this minus in front of the parenthesis means we multiply the contents of the parenthesis by -1. Okay?
Yeah.
So so obviously we convert these two terms, 2y squared and 2xy, into negative terms, and then we're multiplying 3 by -2, so we get, that becomes positive. So, so the very first thing we have to remember, always think in terms of PEMDAS.
Yeah.
And so where we have to change things, we do. Okay, and that's really all that adding and subtracting polynomials is about.
Okay.
Been a hard morning already.
It's
Um,
Monday, that's why.
yeah, yeah, it's yeah, Star Wars Day. May the 4th be with us.
Yeah.
So do you have any questions out of the material we've covered today?
No, I think it's starting to make a lot more sense to me. And I think what helps me a lot too, though, is that I've used it in the workplace without even realizing it was a connection to algebra. But now that I'm also understanding how to use the negatives and positives, it makes it a lot clearer for me.
Super. I'm glad to hear it. Well, I don't have anything else I wanted to do today.
Okay.
So as far as I'm concerned, we can end this a little early. I suggest, that you continue your research, get what you can done before Wednesday, and we'll have a chance to do a lot more practice on Wednesday, and we shouldn't have all the background noise.
All right. Sounds good.
Okay, well, Jennifer, it's been a pleasure, and I'll see you on Wednesday morning.
Okay. Sounds good. Have a good rest of your day, and we'll see you Wednesday.
Thanks, you too.
Bye-bye.
Bye-bye.